This is William Dillon from Electrical Engineering at UTA, and we're beginning our third lecture on complex numbers. This time, we'll be talking about phasor circuit analysis, so we'll finally get into actual circuit elements, and we'll talk about complex power. First, we'll look at the impedance of an inductor. We'll see the circuit symbol for it right here. The little curly things represent the loops of an inductor. The little I is the instantaneous current, the little v is instantaneous voltage, and those are functions of time. In this case, they're sinusoids. We'll look at the current first. It's got a peak value. It's the cosine of omega t plus alpha. If we rewrite that in terms of Euler's function, we write the peak value times the real part of e to the j omega t times e to the j alpha. And that's still a time varying function. It's the same thing as the line above it. Now we go to the definition of the voltage current relationship for inductors. That is inductance times the time rate of change of the current. So we'll take the time derivative of this current by looking at the only time varying function here, which is e to the j omega t. The derivative of that would be j omega e to the j omega t. And so there is our derivative. And if we now convert this to the phasor domain by removing the restriction that we're only doing the real part of this and setting t equal to 0, then our phasor becomes j omega L times I max times e to the j alpha, where e to the j alpha is a complex number, and of course j makes it as an imaginary value. We now define impedance as the ratio of the voltage phasor to the current phasor. And if we carry out that ratio by stacking the voltage on top of the current in this equation at the bottom, then you see there's some cancellation. E to the j alphas cancel, I maxes cancel, and we're left with j omega L as the impedance of the inductor. So it's an imaginary value proportional to the radian frequency. Now let's do an example. Let's take a frequency of 60 hertz. That's a common power frequency in North and South America. And let the inductance be 150 millihenries. Our frequency is omega, which is 2 pi radians per cycle multiplied by 60 cycles per second. The cycles cancel. That leaves 2 pi times 60, or 377 radians per second for our radian frequency. Now, if we multiply this radian frequency times j times L, we get j 377 times 0.150, or j 56.5 ohms. And that will be the impedance for the inductor. You notice it will be a positive imaginary quantity. Here's another example. 400 hertz is a fairly common frequency for power in aircraft and some spacecraft. And the inductance in this case is 85 millihenries. And here again is our picture of the inductor with showing a phasor current and a phasor voltage. The frequency, again, for omega is 2 pi radians per second times the 400 cycles in a second times, well, that would equal 2,513 radians per second for our frequency. Multiply that radian frequency times j and times L, and we get j 213.6 ohms for the impedance. Again, positive imaginary value. Let's look at the phasor diagram between voltage and current for the inductor. If the current were say, alpha radians or degrees from the real axis of the complex plane, the voltage phasor would have to be 90 degrees ahead of it. Remember that phasors are said to be spinning in the counterclockwise direction around the origin of the complex plane. So the voltage will lead the current for a pure inductor by 90 degrees.